from a TT4 average that is lower and lower and lower. So if you take the after-burning section, when you increase the bypass ratio, what's happening? The TT4 average you have is decreasing, and the TT4 prime A you have is increasing. So that means that the m dot FA that you need here will increase a lot. Because you start from a lower temperature and you go to a higher temperature. So the higher the bypass ratio, the more m dot S you have, the m dot FA will increase more and more. And in fact, you can see what are the consequences of what I have just explained. Playing with the bypass ratio, what will you do? You can have, in fact, an increase of TT4 prime A. If you have an increase of TT4 prime A, you will increase, we have explained that yesterday, VJet A. You will increase compared to the turbojet. You will increase FA, but you will increase also m dot FA. And so the question is, what's happening with the TSFCA? Because FA is increasing more than before, but m dot FA is increasing more than before, and as the TSFC is equal to m dot F plus m dot FA divided by FA, what's happening with the TSFCA? It's hard to know. And it's, let's say, rather easy to look at that. So yesterday we said in the turbojet that here we can reach something like maybe 1800K. Here we can go to a higher value, 2000, 2100, even a bit more, depending on the bypass ratio. If you increase the bypass ratio, you increase the TT4 prime A. Okay? And the VJet A, what is the VJet A that you will obtain? We can go here to certainly a speed of 1000 meters per second. 1000 meters per second. And FA compared to F, so FA divided by F, which is related with the square root of TT4 prime A divided by TT4. TT4 prime A, if you take 2000 Kelvin, here the TT4, it is in fact this TT4, the TT4 average that you have reduced compared to the turbojet, And so, how much had we considered yesterday? Let's say 800K, and we are at a lower value, so maybe only 600K here. And you see that you have now something like the square root of 3. Maybe even if you go to 200, 100, 200, 200, because you increase the bypass ratio, it will be here only 500, maybe you have even the square root of 4. And so here, we can have that this value can become equal to a factor like 2. This is quite possible. Why? Because of the increase of the bypass ratio. You see, if you increase the bypass ratio, you have more and more oxygen, you can increase more and more the TT4 prime A, and you decrease more and more the TT4 compared to the value that you had in a turbojet. And you can reach values of an increase of the thrust of a factor 2, increase of the thrust of a factor 2 in a turbofan with, let's say, a high bypass ratio. We will see later on what is exactly a high bypass ratio. Of course, the m dot Fa, so you have the equation of the afterburning section. This is m dot Fa multiplied by QCI multiplied by eta Ca is equal to m dot primary plus m dot secondary plus m dot F, okay, multiplied by Cp of gases, an average value, multiplied by Tt4 prime A minus Tt4 average. What is the situation compared to the turbojet? Compared to the turbojet. So here we have a much higher flow because we have m dot S. And if we increase the bypass ratio, this is even increasing more and more. We have increased the Tt4 prime A. We have decreased the Tt4 average. And even if we increase the bypass ratio, we decrease it more and more. What about this? The eta Ca. Eta Ca is decreasing. Why is eta Ca decreasing? Because you are bringing, so there are in fact there are three effects. One is being discussed by the fact that we have a lower temperature in the combustion equation, but there is a second disadvantage. This is eta Ca. Why? Because you have a lower temperature, and a lower temperature is negative for the combustion chamber, because the combustion chamber is better and better if you have at the entrance a high temperature. It's favorable for the combustion. So second negative effect, it's maybe smaller than the first one. And you see the situation. You have more mass flow. You have a higher difference between Tt4 prime A and Tt4 average, and this is lower. You see that m dot Fa is increasing tremendously, and if you increase the bypass ratio, it is even increasing more and more. We can have situations where m dot Fa is something like 6 times the m dot F. 6 times the m dot F. This is possible, 5 to 6 times. And so, if you take the TSFCA and you take this even equal to 2 times F, turbojet or without afterburning, and if you take this equal to 6 times m dot F, if you take this equal to TSFC without afterburning, you see that now the TSFCA is 3 times the TSFC without afterburning. So yesterday in the turbojet it was only 2 times. And so you see what is globally the effect of bypass ratio, or let's say turbofan, because in the turbojet the bypass ratio is 0. So you can say between the turbojet and the turbofan, what is changing? The bypass ratio. It was 0, it's not 0 anymore. It can be 0.1, 0.2, 0.3, 1, I don't know. And so when you switch from the turbojet to the turbofan, the bypass ratio is increasing and can increase in the different turbofans. And what will be the consequence of the turbofan and in a turbofan of the increase of the bypass ratio? You see much higher gain in thrust. The thrust can increase not anymore by only 50%, but by 100%, but again at the expenses of the TSFCA. It's not anymore 2 times higher, it's now 3 times higher, with an enormous increase of the fuel flow. M dot Fa, 5 to 6 times M dot F, and the sum 6 to 7 times F dot M dot F on the total. Because here it's 6, so there it would be 7. If it's 6 there, it would be only 5 there. And we have created an engine that is, let's say, different compared to the turbojet. Because we have, in afterburning, much, let's say, extreme performance compared to the turbojet. But we are forgetting something. We are forgetting something. This is that we have, thanks to the bypass ratio, a TSFC without afterburning, the TSFC without afterburning, that is, let's say, low. Okay? And that will guide us towards the definition of two, let's say, extreme cases in the family of turbofans with afterburning. I will show you that we can define two families of turbofans with afterburning. So both are turbofans, so mixed turbofans with afterburning. One will be with a bypass ratio that is high, that will be about 1. We can go higher than 1. This is possible. This is existing. If you take engines like the one of the B1, the B1B of the Americans, or of the Tu-160 Blackjack of the Russians, you will have bypass ratios of mixed turbofan with afterburning that are able to fly supersonically, that are more in the region of 2, even 2.5. But these are very rare engines. There are not a lot existing in the world. There are not a lot that they've been developed. But it's existing. But I'm not really discussing these engines that are very special cases. But I'm discussing around 1, and then I will take another turbofan, which is around, let's say, 0.2, 0.3, maybe 0.4. So almost a turbojet, almost a turbojet. Why not a turbojet? Because in the bypass ratio that is very low, let's say even 0.2, you will have fresh air to cool down the external side that we have here. So it will be positive to have a bit of fresh air. What is the advantage of this one? The TSFC without afterburning is low. So this will be a very good engine for, let's say a very good engine, a rather good engine for subsonic flight. Okay? So this aircraft equipped with a rather high bypass ratio around 1 mixed turbofan with afterburning is able to fly with a rather low TSFC in subsonic flight. Okay? And we'll have, due to the high bypass ratio,